Okay, so hello and welcome back. So now let's do a couple more of these examples, probably two of them, and then we will finish this with, we will finish basically the story of transistors here for now. So now let's say that you have a circuit like this, for example. You have this circuit over here, and this goes to a resistor, essentially the same type of circuit that we had in the previous videos. And this goes to the negative rail, this is the positive rail, and from here you connect this to a transistor, and this goes to the ground. And let me say that this is positive V of S and this is negative V of S. And let's say that this goes to, and this is your resistor, and this is your V of C, the collector voltage of this transistor. Let's see that this R of C, and let's call this, for example, R1, and let's call this R2, right? So this is the circuit that we have, and let's say that basically R of C is equal to 1 kilo ohm. R of C is equal to 1 kilo ohm, and your beta is equal to 100. And of course you need to, okay. So now we essentially want to turn this transistor on, right? So how do we do that? So to turn this transistor on, you essentially want to, V of S over here is 10 volts. This is a 10 volt supply voltage. So in order to turn this transistor on, you want basically the whole supply voltage to be dropped across this resistor R of C. That means that if I apply the Ohm's law to this resistor over here, I can say that basically V of S, let's say that set the voltage on this resistor to 10 volts, and basically the current going through that we will calculate times basically R of C. And that means that R of C is the same thing as basically 10 volts to I. And R of C is the same thing as 1 kilo ohm, which is 10 raised to the power 3 ohm, which is the same thing as basically 10 volts to I. That means that this I is the same, I times 10 raised to the power 3 ohm is equal to 10 volts, which means that I is the same thing as 10 volts divided by 10 raised to the power 3 ohm. And then you can simplify this 1 over 10 raised to the power 2. This is 100th, 0.001, basically 0.01 amp. So that's the current going through this branch over here. That means that if you have this current through this branch, the whole supply voltage will be dropped across this resistor, which means that the transistor is turned on, right? So that means that this current over here, I of C, let's say, I of C is the same thing as 0.01 amp. So that's one thing. And then what you can do is that you can calculate the current required for the base of this transistor. And basically, you know that basically this current comes in here. If you close the switch over here, current comes in here, let's call it I1, and at this point it goes into this transistor, which is I of B, and it goes down here as well, which we can call I of 2, right? So now we need to know how much current we need on the base of this transistor so that the collector current becomes 0.01 amps, or basically 10 milliamps basically. Knowing that the beta is beta is supposed to be actually 100. I apologize for this. Beta is equal to 100, right? Okay, so then basically what we have here is if I say that, I can say that I of C to I of B is the same thing as beta, and I know that I of C over here is 0.01 amps divided by I of B is equal to beta, which is equal to 100, which means that 100 times I of B is equal to 0.01 amp, and that means that basically I of B is equal to 0.01 amp divided by 100, which is 0.0001 amp, which is basically 0.1 milliamp. 0.1 milliamp. So that means that I of B is equal to 0.1 milliamp, right? So that's your base current. So now we agreed that we would set this I of 2 to 10 times I of B, which means that I of 2 is going to be equal to 10 times this, which is equal to 1 milliamp. And since I1 is the sum of these two currents, I can say that I of 1 is the I of B plus I of 2, which is 1.1 milliamp, right? And now we have all of these currents, and as a result we can calculate the resistors. To calculate the resistors, I apply, for example, the Ohm's law to R2, V is equal to IR, and the voltage across this resistor is 0.7 volts, and the current going through that is basically this I2, which is 10 raised to the power negative 3 amp, 1 milliamp, times R2, which means that R2 is the same thing as 0.7 volts divided by 10 raised to the power negative 3 amp, which is the same thing as 0.7 into 10 raised to the power 3, basically volt to amps is ohms, which is the same thing as 700 ohms. 700 ohms. That means that R2 is equal to 700 ohms. Is equal to 700 ohms. Next, we can calculate the value of R1, which means that we can apply the Ohm's law to this resistor R1. So basically applying the Ohm's law to R1, the voltage across the resistor I can take as the supply voltage 10 volts, and the current going through that I1 is 1.1 milliamp into 10 raised to the power negative 3 amp times basically R1. That means that R1 is the same thing as 10 volt divided by 10 volt divided by 1.1 into 10 raised to the power negative 3 amp, and you can simplify this by, if this goes to the numerator, this becomes 10 raised to the power 4, and 1 over 1.1 is the same thing as 0.9090 and so on and so forth. So I take this as 0.91. I take that as 0.91 into 10 raised to the power 4. Okay, so that is basically 0.91 into 10 raised to the power 4 ohm, which is the same thing as 9,100 basically ohm, which is 9.1 kilo ohm. Of course, this is not in range, but you have to find some good resistor for that. So R1 is equal to 9.1 kilo. That's basically all the values that you would need for this circuit. Let me check my answer here. 700 ohms and let me see. Okay, so the values are correct. There is nothing wrong with them. So let's do one more of these examples and then we will get to AC. So another example that we have here is basically you have basically, let's say that your R of C is equal to 22 kilo ohm and your beta is equal to 75, right? So how do we calculate, and V of S is equal to 10 volts and so on and so forth. So again, you want to turn this transistor on, so I apply the Ohm's law to this resistor R of C. V is equal to IR. I want the whole voltage, the supply voltage, should be dropped across this resistor. So I set this voltage to 10 volts and basically the current for that I don't know. The resistance of this is 22 into 10 raised to the power 3 ohm, which means that I is equal to 10 volts to basically 22 into 10 raised to the power 3 ohm, which is the same thing as basically that's 10 raised to the power 2, and 1 divided by 22 is equal to 0.045. 0.045. So I take this as basically 0.045 into 10 raised to the power negative 2, and that is basically this current going through this branch over here. So I call it basically I of C, and I of C is basically 0.045 into 10 raised to the power negative 2 amps. Right, so this is in amps, of course. So now we know the collector current of this transistor. We can calculate the base current. To calculate the base current, I of C to I of B is equal to beta. That means that I of C is 0.045, and that is in 10 raised to the power negative 2 in amps, divided by I of B is equal to beta, which is equal to 75. That means that 70 times I of B is equal to 0.045 into 10 raised to the power negative 2 in amps, which means that I of B is equal to 0.045 into 10 raised to the power negative 2 in amps divided by 75. Well, 75 is the same thing as, well, 5 times 15, if I'm not mistaken. 5 times 15, and that's basically 45 is 9 times 4. So if I divide this by 5, I'll get a 15 here. Divided by 5, I will get a 9. So that would be 0.009. And again, you can divide by 3. You will get divide by 3. You will get a 5. Divide by 3. You will get 0.003. And so that's 3/5 is the same thing as, now these simple things you need to know. And 3/5 is, for example, the useful things in calculation that basically gives you a lot of possibilities to be able to I mean, then you don't have to use a calculator all the time. For example, 3/5, or what is 1/2? What is, for example, 2/5? What is 3/5? What is 1/6? These simple things you need to know in, for example, in decimal form. And that basically, of course, that you will learn always when you're doing these examples. And as it turns out, in order to basically to have a good base for electronics, you essentially need to do, well, a lot of them, of course. But then once you go through the time, meaning that as you spend enough time with calculation, for example, probably 6 months, a year or so, then you're good to go. You don't have any problems anymore. And of course, you know that mathematics is always important in electronics. Now, 3/5 is the same thing as 0.6, and since I'm dividing 0.003 divided by 5, I will get basically 3 more decimal places, which means that basically 3/5 originally is equal to 0.6. But then, for example, 0.003 divided by 5 would be equal to 0.000 basically 6, I suppose, right? So if I have 0.003 divided by 5, it's equal to 0.0006. So that's the number. That's 0.0006 into 10 raised to the power negative 2 in amps, which is the same thing as basically 0.000006 in amps, which is the same thing as 1, 2, 3, 4, 5, 6. That's 6 microamps, right? So your base current is supposed to be 6 microamps. I of B is supposed to be 6 microamps. Okay. So now we said that basically we would take I of 2 as 10 times I of B, and that tells us that then I of 2 can be taken as 60 microamps, and since I of 1 is the same thing as I of 2 plus I of B, therefore I of 1 would be equal to 6 microamps plus 60 microamps, which is the same thing as basically 66 microamps, right? So as a result, basically what we will have is basically we have all the currents that we need. We can now calculate the resistors. The resistors, basically applying Ohm's law to R2, we have V is equal to IR. The voltage drop across this is 0.7 volts, and basically the current going through that is I2, which is 60 into 10 raised to the power negative 6 amps times R2, which means that R2 is the same thing as 0.7 volts divided by 60 into 10 raised to the power negative 6 amps. And that is the same thing as, well, I can write this as basically 7 into 10 raised to the power negative 1. And then 10 raised to the power negative 1, this becomes 10 raised to the power negative 5. And 7/60th is the same thing as 0.116. So I take that as 0.12. 0.12 into 10 raised to the power 5. Right? And that is basically in ohms, which means that basically you have 12 kilo ohm, right? So this is the same thing as 12 kilo ohm. So that means that R2 is supposed to be 12 kilo ohm. And then you can apply the Ohm's law to this to resistor R1, which gives you basically the voltage drop I take as 10 volts across R1. I'm ignoring the voltage drop across R2. So 10 volts is the same thing as the current through R1 is I1, which is 66 into 10 raised to the power negative 6 amps times R1, which means that R1 is the same thing as 10 volts by 66 into 10 raised to the power negative 6 amps. And 10 divided by 66 is the same thing as 5 to 33. And 5 to 33 is 0.15 and so on and so forth. So I take this as 0.15 into 10 raised to the power 6. And that is in ohms, which is the same thing as 15 and 4 zeros in ohms, which is 150 basically kilo ohm. That means that R1 is supposed to be 150 kilo ohm. So that is the values of these resistors that we are supposed to have. So this was question number 11, 11.7 kilo ohm, 12 kilo ohm we got over there, and 141 kilo ohm we got 150 kilo ohm, which is correct, give or take. I basically, depending on whether you ignore the voltage drop across the PN junctions and all of those things, the answer is correct. Okay, so the next thing that we have here is a little bit of AC, and AC is always exciting because you get to work with oscilloscopes, and you have to do a lot of that, and you get to work with reactance and inductance and capacitance and all of those things, but then in AC circuits. In AC circuits, things are going to be a little bit different. Up to now, we were in DC. In DC, things are simple. The conditions are kind of man-made in DC. I mean, in DC, you have the voltage as a straight horizontal line going through the basically in DC, basically everything, if this is voltage and this is time, the voltage is basically always something like this, which is, of course, there is some ripple on it, but the ripple most of the time is negligible. You wouldn't even see the ripple in DC. But and by nature, basically a DC voltage makes everything simple because there is no fluctuation in your voltage, of course, as far as you're concerned and as far as your applications are concerned. There is always basically, again, a ripple on your DC, and every DC, when you look at it, you will, and I'm not really sure about this, but every DC, I'm using the word every, but probably 99.9% of the time, any DC voltage that you look at, you will see some ripple on it. That means that every DC you can say is pulsating DC, or is some sort of AC voltage changing with time. But then when it comes to AC, things are different, because then basically you will get to work with, because you have then to work with basically all of these, let's say this is, for example, pi by 2, and this is pi by 2, this is pi, and this is 3 pi by 2, and this is, for example, 2 pi, and then you have basically a sine wave like this. You will get a sine wave like this. You would have something like this over here. So your voltage is always either something like this, or it is some voltage, for example, something like this. There is many different types of AC, of course. And so this is constantly changing, and it makes everything a little bit more complicated. And then there is also then in capacitors you will have reactance and inductance and all of those things. But it's very exciting, and we will work with them as we go along. So I hope that you enjoyed this video, and in the next video we will have a short discussion of basically of AC, and then we will start doing some problems, probably doing some I don't know, probably doing a couple of things on the bench, taking a look at a couple of waves or things like that. Let's see how that goes, and then basically when we get into AC, then we will know more about basically different types of filters, low pass filters, high pass filters, and that sort of thing. And then you can, for example, use all of this in radios or in different basic areas. Right? So I see you in the next video with AC, and thank you.